got my wooden block, and right before class, I checked it had a mass of about 30 grams, and it has a volume of 4 centimeters by 4 centimeters by 4 centimeters. 4 times 4 is 16, times 4 is 64. So it's 64 cubic centimeters. So is the volume exactly that? No, but it's pretty darn close. One edge seemed to be like 3.95 centimeters, but only a little bit of wood. And as far as the 30 grams goes, could have been 31 grams, maybe it was 29. I'm pretty close there too. So mass and volume are related to another very important idea in science. Anybody want to take a guess at what it is? Density, yes. So density is the amount of substance something has, its mass, and how it's spread out throughout its volume. So just mass over volume. Things can be densely packed together and heavy, or they can be not so dense and light. So wood's kind of light, right? If this was made of lead, it would be way heavier, right? Which means there's more mass crammed in the same space, so it's denser. So let's calculate the density here. So my mass was, again, 30 grams. So in this case, density is grams per cubic centimeter. Anybody with a calculator, help me out. What is 30 divided by 64?
0.4. Oops, sorry. 4. I'm just going to say it. Sorry. 0.46875.
6875, and that would be grams per centimeter cubed, the units of density in this case. All right, so we have 1, 2, 3, 4, 5 decimal places. Okay, so, all right. There's probably some really sophisticated piece of scientific equipment that can somehow measure the density of this thing, but the simplest way to do it is just mass over volume. How confident are we in my measurement of the mass? Did anybody watch me do it? Anybody see how good my equipment was? Okay, so I had a 40-year-old balance beam scale. Works pretty good. It's not one of those fancy digital scales, but it's one of those scales that you have to balance before you can use. And then the volume, anybody measure this? You guys just looked at it. But yeah, Alex, you're right. Well, let's call it 4 centimeters, right? And I did measure it, but you think all these sides are perfectly flat and, you know, there's some room for error there. So the question is then, how certain are we of all those decimal places? Are we really sure Gary measured everything to be accurate to 5 decimal places of accuracy in this?
Because there's a huge room for error.
Yeah, I had a lot of room for error when I was measuring the weight, when I was measuring the volume. So now we have to look back at the numbers we started with and say, okay, what numbers are we certain about here? So the 64, are we pretty sure about the 6 and the 4 there? Could one of them be a little bit off? Now, I'm pretty sure the 6 is right. The 4, more or less. Pretty close. 30 grams. I'm pretty sure about the 3 and the 30, but the 0 might have been just a fraction more. Tiny bit. So my guess here is looking at each of these numbers. Let's say I'm confident of that one. And I had a heck of a guy at the mill that made this block. I'm actually confident in both of those. The rule with significant figures is you have to go with the least number of digits in any of the numbers you started with. Which means, how many significant figures do you think I have here? I only have 1. Okay. I have to go with the least significant figures in the numbers I started with. Okay. So although this one I think has 2 significant figures, this one only has 1. Therefore, in my answer, I can only be assured that one of those numbers is right. Everything else is questionable.
So if you were, I'm lost. I don't even know how to act. I'm just lost.
So bottom line is, I took two numbers that I measured.
Okay.
And I had some confidence in each of those figures. In the first one, I was confident in one of the decimal places. And the other one, I was confident in both of them. But then I threw them into a formula that ended up dividing them. That division led to a whole bunch of place values. So based on the numbers I started with, this is what significant figures are about. Based on the numbers I started with, there's a degree of uncertainty in some of those places there. And so my original numbers tell me how much I can be certain of in my final answer.
So if you had like,
If I was confident of the
164,
3 and the 0,
you'd have the 4 and the 6.
then I would say the 4 and the 6 are significant here.
Okay.
So it could be on my scale that it was 30.00 something, right? So the next place I wasn't sure about, but I was sure about the 3 and the O in the way I was reading its mass.
Okay.
Then both of those were certain, and both of those were certain in my measurements. And it was that point whatever grams I was unsure about, or point whatever cubic centimeters I was unsure about. Then I have two significant figures in both of them. That would give me two significant figures in my answer, and I could go for both the 4 and the 6 in the answer. So significant figures is looking at the numbers you started with, doing a calculation with them, and then saying, okay, in the result of the calculation, I can't be sure about all of these values, but based on what I started with, I'm going to say I'm sure about 2 of them, which is a different idea than, for example, these are both whole numbers, right? There's another school of thought in terms of calculating an answer that says you can go one more place value than what your original numbers had. What's the smallest place value in my original numbers? The 1's place. Okay. So then this other school of thought would say then, well, when you do a calculation with those numbers, you can't go any more than the 10th spot. Otherwise, you don't know. You're reaching out in places you don't have enough knowledge of. So that other school of thought would say we would have to stop at the 4/10, maybe round it to 5/10. So in some sense, we think about approximation as a pretty straightforward thing. We think of the idea of rounding. And there are rules for rounding. We're all really good at that. Kids get good at it with whole numbers. It's no big deal doing it with decimals. So rounding is one thing we do. Another thing we do is called truncating. Truncating is we just chop stuff off. We don't really care about what the next digit is. So a minute ago, we had the number 0.4675 or 875. 875. I could round this to the nearest tenth. And I would say this is approximately wavy equal sign 0.5. But with significant figures, if you're not sure about other digits, if they are questionable, you can't use them to round because they're questionable. Maybe that 6 was supposed to be a 5. I don't know. It's beyond my knowledge. So sometimes instead we have to truncate. And so with significant figures, I'd have to say it's 0.4. I just chop because I'm uncertain of what comes next. So significant figures is all about whatever certainty or uncertainty you think is going on based on the original measurements. Okay. And think about things a bank does. When banks make calculations, does it always come out to a whole number of cents? When we apply tax, does it always come out to a whole number of cents? Sometimes we round when we do those financial calculations, but there are other times we just chop off the extra stuff. And the big question is, well, where does that extra stuff go then? Okay. So with this in mind, the book was kind of light on this area. In the latest revision, I added 2 sections. There's a reading about significant figures here, and then there's a different online homework system than we've been using. I don't know if it's going to work though, so this is an experiment. You guys are going to report back to me on this. I'm using a system called CK12 here, which is a free K through 12 and a little bit of college. They have online books, they have videos, and they have a bunch of different kinds of interactive online homework things. Sometimes some of them are like games, some of them are like the homework you've been doing. You know, it's fill in the blank or it's multiple choice, things like that. There's a possibility when you guys try it that it will ask you to sign in on the practice and then it will send a grade back to Canvas. There's also a possibility that will not happen, in which case you can just report back to me on how you did it. Okay. So give that a shot. Yeah. So, oh, I see what you're saying. I don't know. So let's see. So if I go into student view here, I don't know if it'll work for me in student view. When I go to this one right here, it'll take me to the reading, I believe. Yeah, so what it does is it loads the CK12 stuff inside of Canvas. And just like the connection is kind of weird with our Pearson stuff, I'm not sure what's going to happen here. So I went over a bunch of this stuff, but I'd like you to look at it again here. And then next, it should take us into the practice. And since I already have an account here, is it going to see me as me? Or is it going to see me as some student? I don't see a sign-in. Start practice. And these are linked back to that reading, and there's a slightly different reading here that's short and nice. Yeah, I don't know what's going to happen when you guys do it. Me as a test student is a little bit different. Okay, but try it out. There's a little practice with significant figures there.
I was looking at the online homework earlier, and it said that the 8.1 homework was due on Wednesday.
Yes, we are going to go over that today.
Okay, I wasn't sure if that was like a typo or what.
Yeah, so and I'll explain that in just a minute. Okay, so I'm going to stop on 7.2 right now. I'm going to start talking about 7.3. We'll take a look at that CK12 stuff. If you could look at it between now and the next class, I'd appreciate it. And then we'll talk about how it went. So 7.3 is about repeating decimals. That don't end. And I decided to link this with 8.1. 8.1 is, it's called real numbers, but mainly it deals with a type of numbers called irrational. And I mentioned irrational numbers in this class a couple of different times. And irrational numbers are essentially, they can be viewed as decimals. The decimals don't end and don't repeat. I'll put a question mark on that because that gets a little weird. And I thought these two fit good together. And otherwise, in chapter 8, we're really not going to do anything else. Section 7.4 is about percentages, and that is just a slightly different topic using decimals. But 8.1 and 7.3 work well together because they're two different sides of the same coin. So we've got division down. We played this a little while before. 1/3 is a decimal we played with. Using long division, we know that that's equal to what is a decimal? And the 3 keeps on going forever and ever and ever. Right? When I break that out in terms of its place values, I have 3/10, and I have 3/100, and then I have 3/1000, and that just keeps on going and going and going. Okay. I mentioned some other cute fractions and decimals. 2/9, for example. I think I might have mentioned that last time. It's not 2/3, 2/9. Anybody remember what that is or have a calculator nearby?
2.2.
Here we have 0.2222. That just keeps on going. So guess what 5/9 is going to be? That's going to be 0.5 repeating. 5/10, 500, 5,000, and so on and so on and so on. Note that 1/3 is also the same thing as 3/9. Hence, the numerator repeats when you divide by 9. Which leads me to an interesting question. If 2 is in the numerator and the 2 repeats, and 5 is in the numerator and the 5 repeats, if we put 9 in the numerator, do we get 9 repeating? Forever and ever?
1.
We get 1?
Yeah, because 9/9 is 1.
So is there something wrong with this pattern on the right? He looks puzzled and thoughtful. Emily, what do you think? You're rounding it to 1? Okay, so question. Do you accept this as fact or is that questionable too? You accept that as fact. Do you accept this as fact? Okay. But you're struggling with that one right there and it meets the same rule. Yeah, so let's take a little farther. Let's take 1/3, which we know to be what again? 3 repeating, so 3/10, 300s, 3,000s, and we just keep going on like that. And then let's see, 2/3. What's 2/3? 0.6, 10, 600, 6,000s. Every single place is going to have a 6 in it, correct? Yeah. And then for fun, what we're going to do is we're going to add these two lines together. Let's see what we get. 1/3 and 2/3 is 3/3 or 1. And let's see, no tenths, no whole numbers. Let's see, 3/10 and 6/10 is 9/10 and 300s and 600s is, and 3,000s and 6,000s is, and I'm going to keep doing that forever. Okay, so if you accept that 1/3 is 0.3333 with the 3 repeating forever, and 2/3 is 0.6666 with the 6 repeating forever, then you now, I think, kind of need to accept that 1 is the same thing as 0.9999999. Kristen looks miserable for that one.
Yeah, bring more chocolate.
You need more chocolate for that one. It's a weird idea, isn't it? How many, I think, I got a feeling that everybody's mind right now is rebelling against this. But you're unwilling to let go of that fact that you learned, which is analogous. Okay, I'm going to leave that alone for now. I'll let you mill some more. We'll talk about it next class. All right, so let's keep going. How do I know what a repeating pattern is? How do I find a repeating pattern? Refine repeating patterns and decimals. And hopefully you remember this from about a week ago. Or I should say repeating, yeah, decimals, that's okay. So we're starting with fractions. Like we looked at 1/7 a week or so ago. Calculator. Now this is one I thought was so cute I chose to memorize it. 1, 4, 2, 8, 5, 7, repeat. And the way we find them is by doing long division with decimals.
Don't you wait for the remainder to repeat itself?
Yeah, you need the remainder to repeat, not the numbers in the quotient here. And these are the numbers in the quotient here. Those aren't as significant because you can have decimals that look like this, 0.1212. Ah, we think we got it. But then all of a sudden it goes, and then only the 3 repeats after that. That number exists, it's a number. We can turn it into a fraction. It's not gonna be a very nice fraction, but it exists as a fraction. Okay. So we can't just rely on saying, aha, I got you now, because then all of a sudden it can do something. But once we see a repetition in the remainders, then we've got it nailed. Because once we see a remainder, that same pattern of remainders is going to happen again. Related to that, any particular divisor, like 7, has at most 7 remainders. When we do division, you could divide 7 in and have 1 as a remainder. You could have 2 as a remainder. You could have 3 as a remainder. You could have 4 as a remainder, or 5 as a remainder, or 6 as a remainder. Can you have 7 as a remainder? No, that means you didn't look for enough 7s, but you could have no remainder. Now, if you had no remainder, it ended. So in terms of decimals that are going to repeat, it's always going to be at most 1 less place than the number itself. Okay. So if we call 7 our n, then a number called n can go out at most n minus 1 times before repeating. And most numbers do it well before n minus 1 times. Like 9, how many times does it go before it starts to repeat? 1 place. Anybody remember about 11 the other day? It went out 2 places. It had the potential to go up to 10 based on this idea right here. But, and I don't know the answer to, like, how can you tell how many times it will go out? I think that's an unanswered question, but I'm not positive. I looked at a number, I think it was 41, and I think it went out 30-something times before it repeated. I was really bored reading one day. It was a very long division on a sheet of paper. I think I had to tape a couple together to make it happen. So it's kind of a cool thing. Some other things we've answered, when you're going to have a repeating decimal and when you won't based on a fraction. Remember we talked about that a while ago? Let's see if we can remember. So let's see. Denominators will either terminate or will end up repeating.
Isn't it 2 and 5 is the terminate?
Yeah, anything based on 2 and 5s terminate. So if it's based on 2 and or 5 only, yeah. Can only 2s and 5s as factors, it's going to terminate. Everything else repeats. So numbers like 2, 4, 8, any powers of 2. 5, 25, 125, powers of 5. 2 times 5 is 10. So 10, 20. Ooh, that light is getting in the way.
So my question, on the homework we had, the question was if 34 was a terminating.
Yeah, well, 30 be a term. Yeah, 34.
But I did like the whole prime factorization of it.
Yeah, so 34 is what? 2 times 17?
But because it has 2, then it would be.
It can have only 2s though. Since it has a 17,
Okay, that's what I
it's going to repeat most of the time.
Unless the numerator cancels it out.
Yeah. So I noticed I put can and not will here. So suppose my denominator was 34, like you said, 34 is 2 times 17. So most of the time, like 1/34, that is going to repeat forever. 2/34 will repeat forever. 3/34 will repeat forever. But when I get to 17/34, 17/34 reduces down to 1/2, and so it terminates. Okay. So sometimes, so it doesn't mean it's going to absolutely repeat. It depends if the numerator takes out the troublesome factor in the denominator. Okay. So just a simpler example of that would be to think about sixths. 1/6 is 0.16, and only the 6 repeats. We can see that for sure when we do long division by taking 6 into 1 and then putting a point and some zeros to see what happens. So 6 goes into 1 0 times, decimal point. 6 goes into 10 once, subtract, and I get a 4, bring down the 0. 6 goes into 40, 6 times 6 is 36. Subtract, I get a 4, and there is my repeating remainder. And so it's stuck in that loop right there. So that right there tells me only the 6 is going to repeat. Two 6 reduces down to 1/3. So it's got a slightly different repeating pattern. But what about 3/6? That happens to be 1/2, and it terminates. And so it kind of depends on the numerator. But the bottom line here, what is causing the trouble with sixths?
Is it anything that reduces
3. What's that?
down? Is it anything that reduces down to like 1/2 or a fifth?
As long as the numerator cancels out everything that's not a 2 or a 5 in the bottom. So suppose we had, let's see, what's 2 times 3 times 7? That's 42. So if 42 was the denominator, the only time this wouldn't repeat is if both the 3 and the 7 get taken out of action by the numerator. So if you have 1/42, nothing cancels. It's gonna have some repeating pattern. 2 out of 42. Does 2 cancel with the 3 or the 7 there? Answer is no, so that means it's gonna have some repeating pattern. 3 out of 42? That cancels part of the problem. That's gonna make it repeat, but the 7 is still hanging out there. So the only time 40 seconds are not going to repeat is if you can get rid of the 3 and the 7. What could my numerator be to get rid of the 3 and the 7?
21.
Yeah, 21. So anything related to 21 in the top, any multiple of 21, will cancel out the 3 and the 7, and you'll get something like a half in this case. Okay. So it depends on how the denominator factors. The only way it's not going to repeat is if you remove everything that's not a 2 or a 5 as factors. That answer your question? No. Okay, try again.
I just don't think I'm getting it. Okay.
About when they will
Yeah.
repeat?
Like I get that 3 and 7 go into 21.
Yeah.
But it doesn't make sense to me, the whole process.
If you factored out like both of the numbers, just like if you factored out the top number and then the bottom number like separately, you could see like the prime
21 is
factorizations.
3 times 7.
Well, I get that
Yeah.
part. I don't get where, the only thing I don't get about this, I just don't think I'm getting it.
Okay.
Because it
So,
still doesn't make sense.
okay, so a couple of things. Have you read the book yet?
I read the part on how to do like the non-repeating and repeating, but I don't.
Okay, so do some more practice and we'll look at it again on Wednesday. Hopefully it'll start to make more sense. And then I'm also going to want you guys to work on activity 9 for homework. Okay, so let's do a couple more problems. So we've got a rule that tells us when things repeat and when they don't. And that has to do with the factors in the denominator. Okay. Now that's starting with a fraction. the next question is taking a decimal, like let's try 0.123, 123, 123. And so only the 1, 2, 3 repeat. How do I figure out what fraction that is? So we're going to take it the other way. Okay? So before we do this one, I'm going to do a slightly easier one. I'm going to take one we already know the answer to. So let's take 0.333, repeating forever. So let's suppose we don't know what fraction that is. One way to solve it would be to say, okay, let's just call that fraction x for now. And then what I do is I look at 10x. The reason I'm looking at 10x is because we're repeating only after one place. Okay? It's a pattern of 1, not a pattern of 2 or a pattern of 3. So what's 10x equal? If x is 0.33333, it would be 3.333, repeating forever. Once I have that, then what I'm going to do is I'm going to subtract the original number on both sides of this equation that I built. What's 10x minus 1x? That'd be 9x's. And then here, 3 minus 0 is 3, but 3/10 minus 3/10 is 0, and 300ths minus 300ths is 0, and 3,000ths minus 3,000ths is 0. So what's the new pattern in the decimals? Just a whole bunch of zeros. So the problem here is this infinite repeat. And so this trick right here allows me to subtract out that infinite stuff that's driving me nuts, because I get it to match up. So now I've reduced this down to 9 times my missing number has to equal 3. How do I get my missing number back? I just divide by the 9, so x has to be 3/9, which we can then reduce down to 1/3. So we're going to try this again on my crazier number. All right, so 0.123, 123, 123, and it's just going to keep going 1, 2, 3. How many places are repeating here? Yeah, 3 places, so we multiply by 1,000. I'm going to call this number x, and I'm going to create a new number called 1,000x. Which would be 123.123, 123. And it keeps going like that. Rewrite the original number underneath. And we're going to subtract it on both sides. And this is just a fun trick we get to play with infinity. So I have 1,000 x's, I take away one of them. How many x's do I have? 999 x's, and on the other side, that crazy infinite decimal disappears because they line up perfectly. And all I'm left with is a 1, 2, 3. So now my answer must be 123 over 999. Now that may reduce. Sometimes these reduce, sometimes they don't. This does reduce because 3 plus 2 plus 1 is 6. So 3 is going to go into top and bottom. Did you already reduce it, Ashley? What'd you get?
41 over 333.
41 over 333, and I'm pretty sure 41 is prime, so we're done.
So I have a quick question.
Yeah.
So how are you getting 123 over 999? Because if you do normal.
So right now.
Oh, never mind. I get it.
You get it now?
I did it wrong. Yeah,
Okay.
I did it backwards.
Okay. Yeah. So I'm dividing both sides by the 999.
I think I'm just fried because I tried to take 123 under.
To do it backwards.
Yeah.
So just double check on your calculator. Take 41, divide by 333, and hopefully it goes 1, 2, 3, 1, 2, 3, 1, 2, 3. Now here's a wicked cool thing about having nines, or a bunch of 9s as digits in your denominator. Oops. So let's take 9,999, and then Nikki, give me a 4-digit number.
1,234.
1,234, excellent. So whip that out on your calculator. What's 1,234 divided by 9,999?
1, 2, 3, or, wait, 1, 2, 3, 4, 1, 2, 3, 4.
Yeah, the numerator is just going to repeat over and over again. It's this wicked cool property about just having 9 in every place value in the denominator. Suppose instead we had 25 over 9,999. Anybody want to try to predict what that's going to be?
0.00025.
Almost.
Like 0.002. Like one too many zeros.
And it's just going to, it's just going to keep going like that. So check on your calculator, take 25 divided by 9,999. Which is kind of cool. So that trick we did over here is kind of related to that property right there. And we are about officially out of time, and Kristen is fried today, so we better stop here. So I didn't get quite as far as I wanted today, but that's okay. So what we've done is we've finished up section 2. You may still have some homework to finish. I accidentally set the due date for that last week. I apologize for that. I reset it tonight. If you want more time, let me know. And then we started covering 7.3 here. We're mostly done with 7.3. Activity 9 is related to this, so start looking at activity 9 for homework, and we'll tie that up in class on Wednesday. And then 8.1 is about numbers whose decimal go on forever, but don't repeat. And I talked a little bit about those a week or two ago, and so I'll talk more about them in the next class. And then we have percentages to do, and then we have to decide if we're going to have one more test or just a final exam. And I'll talk to you guys about that on Wednesday. I have a couple
We
of
only have
ideas.
4 weeks left.
I know.
Finals, right?
We only have 4 weeks left. Yeah, this is the 7th week of classes. It's
it's
going
faster
by
than
fast for
last
me.
year.
You're teaching the next course, right?
213, yeah.